Good morning, everyone. Morning time in Sydney, and it's currently February. In preparation for FiLPART in India, I'm going to take you through some of the prerequisites for our special seminar on higher algebraic K-theory for Leavitt path algebras. The first half of this is what I'd say is essential things on I guess the properties of Leavitt path algebras relevant to us, and also some basic content on projective modules. If you're familiar with this already, you probably won't need to watch this. And the second part will be on, well, things I find interesting that might be of use to you during the seminar, but it's by no means necessary that you watch it. So if you have the time, I'd love it if you were to listen. So I've just got my notes here on the left, and I'll be writing things that I need to write out on the right. So throughout K, the little k, will just be an arbitrary field, and R will denote an arbitrary ring or K algebra. If I ever use little e and little f in R, it'll usually refer to idempotent elements. So if you recall, idempotent just means if you square the element, you get back the element you start with. And if I have a tuple, E0, ERS, E1, RS, this will refer to a quiver. So if you recall, the idea of a quiver is, let me see if I can write this out. Does this work? Yeah, perfect. So if you have a quiver, recall that's just essentially a directed graph. B1, B2, B3. So E0 would refer to the set of vertices, V1, V2, and V3. E1 would refer to our edges, E and F. And the range and source maps will be the functions that go from edges to vertices, and they spit out the head or the tail. So the range of E would be the head of E, which is V2, and the source of E would be B1. And P and Q will usually denote finitely generated projective modules. So we're going to talk about what projective modules are. So there's lots of equivalent definitions in the literature. This is the standard definition that you'll see in any textbook. We're not going to prove this lemma. It's a good exercise, one, and two, many other texts out there will explain it better than I can. So if you Google any learning material out there on projective modules, they should all include this result and a proof of it. See, the essential idea with the projective modules that if you have it has a lifting property. So if you have a surjective map of modules here on the right and a map from your projective module P to N, then it should always admit a lift, making everything commute. The main, at least in practice for what we're going to be doing, the main property or defining property that's relevant is the second point, that it's a free summoned, sorry, it's a direct summoned of a free module. So yeah, have a go trying to prove that these definitions here are all equivalent. If you want to have a turn, the way I recommend you do it is first show that 1 and 4 are equivalent. Second, what would you do second? I guess 1 implies 3. That's a pretty obvious one if you spend some time thinking about it. Third, try and show that 3 implies 2. And fourth, you should be able to do that 2 implies 1. So yeah, if you're not familiar with projective modules, I recommend you try this exercise for a little bit. And if you can't do it, don't worry, just Google it. And it'll be a good learning exercise for you. So throughout what we're going to be doing in over the early part of April, we'll always be assuming that our projective modules are finitely generated. Because essentially we want to study how our projective modules behave under direct sum. And if you allow infinitely generated things, for reasons I'm not going to get into, it's not really that interesting to work with. So if you just restrict our attention to finitely generated projective modules, it's much more interesting, the theory, and so that's what we'll be doing. So we'll always assume that our projective modules are free summoned of a finite, a direct summoned of a finite rank module here. And what you get from that is if you have, say, Rn is isomorphic to a direct sum of P and Q, then you have a projection to P, which we'll just call pi, and an inclusion back into Rn. So this composition here, projection to P and then inclusion, should be idempotent. And conversely, if you include into Rn and then project back onto P, that should be the identity. In other words, this projection admits a section I. But this here is important because it basically means that you can always write your projective module. So I'll put it in green here. Projective modules can always be written as the image of an idempotent matrix. And notice to make this statement here, we do need to assume that our projective module is finitely generated to draw from Mn here. Otherwise, you have to do infinite matrices, and it's quite ugly. So, and you can also look at this remark here, which I quite like. So if you have an idempotent matrix, n by n matrix, the direct sum of its image and 1 minus its image is the entirety of Rn. And the image of 1 minus E is the kernel of the idempotent matrix. And if you don't recall this, that's okay, but it's important for us to know that if E is an idempotent element, then 1 minus E is also idempotent. And they form something called mutually orthogonal idempotents. So when we do K-theory, we'll be interested in studying the monoid of finitely generated projective modules. So we always have this P of R here, which is a monoid under direct sum. Projective modules. And the addition rule is just direct sum. Actually, what's a better way of writing this? We're interested in isomorphism classes. So I guess I should write the rule for classes. So if P is an isomorphism class and Q is an isomorphism class, then their sum in the monoid is the isomorphism class of the direct sum. It's good for me to be specific when I speak here. The example for you to think about, if you have just a field K, and we're interested in the finitely generated projective modules over K, I'm claiming that this monoid here is isomorphic to the natural numbers under addition. I'll give you a moment to think about it. You can pause the video. But the answer is that all projective modules over a field are free. So summing two projective or free modules over K really just amounts to adding their dimensions together. And so the monoid, the only interesting part of the monoid is the dimension. And since dimension comes in natural numbers when everything's finitely generated, that's the answer there. You can replay that a few times if that wasn't clear. So the 0th K group, we call the Grothendieck group. It's the group completion of this monoid here. So same rule as the monoid, but we now turn it into a group. So if you recall what a group completion is, I'll just write it here. It's exactly what you think. You kind of add elements and you also kill certain elements in your monoid to make it in a group in the most universal way possible. Is the universal abelian group such that for all, I guess, monoid maps, so if we have a monoid map from the monoid of finitely generated projective modules into an abelian group A, then this will always factor through K of R, K0 of R. So if A is an abelian group and you have a monoid map from P of R to A, then there's this always factors through uniquely through K0 of R. We call this K0 of R the Grothendieck group, or I guess the universal abelian group created out of P of R. So the idea here is that two isomorphism classes are identified in K0 of R if and only if there exists not P0, just P. A finitely generated projective module M such that P of M, well, P direct sum M is isomorphic to Q direct sum M. This is the important part here. And you also have formal differences in K0 of R, but more or less that's the same idea. So go through some examples. If we remember from earlier that the finitely generated projective modules over K are in one-to-one corresponds with natural numbers. If we group complete the natural numbers, you get the integers. Oh dear, what's Bing doing? A bit more of an interesting example, if we have the polynomial rings over K in one variable, then K0 of this ring is also Z. And it's for the same reason that all projective modules over Kx are free. If we want a more interesting example, if we take Kx and we mod out by the ideal x squared minus x, then K0 is now Z2. To see why, it's basically in this new ring here, just scroll down a bit. In this new ring here, x and 1 minus x are mutually orthogonal idempotents. Mutually orthogonal idempotents. So what that means is x squared is equal to x, 1 minus x squared is equal to 1 minus x, and x times 1 minus x is 0. So if you recall earlier, the projective modules are just images of idempotent matrices or maps. That's essentially what, if we just have the 1 by 1 matrix X, that's an idempotent matrix, as is the matrix 1 minus X. So, and these form each of the generators in this C2 here. And for a really disgusting example to show you that there is something interesting here, if we take this really big ring here, so we have the free algebra on 4 elements, so we don't assume these elements commute anymore. Sorry, alarm's going off. Give me for that. So if we have these 4 free symbols here which don't commute, and we impose these very specific relations here, you can get a ring whose K0 is 0. And to explain why that is, I basically chose these relations here perfectly. I cooked them up perfectly so that we have these very specific matrix relations. So if you have the 1 by 2 matrix AB and the 2 by 1 matrix CD, if you put them together like so, you get the 1 by 1 identity matrix. And if you swap them around, you get the 2 by 2 identity matrix. So you can check here that my relations up here assure me this. Now that is to say that AB and CD are mutually inverse matrices. And so they actually form an isomorphism in this ring R between the free module of rank 1 and the free module of rank 2. So as R modules, R is isomorphic to R2, which is pretty wild if you think about it. And so what you have in the ring, that this R2 is just R plus R, so you have 2R is equal to R. That is to say, if this is an abelian group, the only way this is possible if R is 0. The class associated to R is 0. And that basically kills everything here. So everything's just 0. The nice thing, you basically have I'll talk a little bit about the invariant basis number, or the IBN. Oh. Invariant basis number. So a ring has the IBN. R has IBN if Rn and Rm are isomorphic as R modules, if and only if n equals m. When I was first learning about this, I thought this was an obvious property because I didn't know of rings like this that existed. But it is unfortunately not the case. It's a very interesting study and largely solved at this point, I'd say, over when rings can or can't admit this property. If you're only interested in the world of commutative rings, you don't have to worry about this. You'll notice here, for instance, that this only works because we assume that these symbols don't commute. In general, yes, if any ring is commutative, it'll always admit the invariant basis number property. But if you're looking in the non-commutative world, you have to be on the watch for things like this. And you can also have rings where, say, the free module of rank 5 is isomorphic to the free module of rank 8, but you don't have anything less than that. And if you look to the K0 group, that'll give you a K0 group that's torsion. And that's also interesting in and of itself. But moving on, so that's kind of the stuff on projective modules I wanted to talk about out of the way. So we move on to Leavitt path algebras. Now, the study of Leavitt path algebras is very well developed. It kind of came into being by two groups of authors simultaneously and independently in the early 2000s, I think. And it's turned into a very big field of study with multiple researchers all over the world, all working on different facets of it, looking at different properties and representation theory as well. So I hope to, over the next few minutes, and also over this school that we'll have in India, to kind of show you why that is and give you a taste of why people are interested in Leavitt path algebras, one of the many reasons. If you're familiar with Leavitt path algebras, you can skip this part, but if you're not, and you can't be bothered to look it up yourself, you can listen to me for a little bit. So if you have a directed graph with our vertices, our edges, and our range and source maps, we can define the Leavitt path algebra as the K-algebra with the free, or I guess you could say the K-algebra on symbols, E0, E1, union E1, union what we'll call the ghost edges. So the idea is here you have the symbols, the associated to vertices appearing in your Leavitt path algebra, and also two symbols associated to each edge, a normal edge and one of these ghost edges. And they're subject to the following relations. So if you have two vertices, V and W, if you multiply them together, they give you V if V is equal to W. So all these vertices are idempotents. And if they're not the same, they give you 0. So all vertices are mutually orthogonal idempotents in this algebra. Another property is if you have an edge E and you multiply on the front by the range of E or on the back by the source of E, you'll just get E. And you have the same property for your ghost edges, but swapped around. So you can think of your ghost edges as going in the opposite direction if you're familiar with the idea of what a path algebra is. Another property we have, and these properties 3 and 4, I'd say, are what make the Leavitt path algebra especially interesting. If you have a ghost edge, E star, and you multiply by F, if E is equal to F, you get the range of E, so the vertex. And if E is not F, these multiply to give you 0. And if you have V, which is not a sink, so there is an edge coming out of it, that's what this little thing here means. So if you have at least one edge coming out of V, you take the sum over all edges coming out of V, and you put E star. So to give you a concrete example of that last property, if we have the E and F, E and F are the edges, and we have a vertex V here, then in the Leavitt path algebra, this relation will be present. And I guess I'll also, oh no, I've already written all the other relations out. So as an exercise to you to get familiar with this, it's pretty easy. You just have to use the first two relations here. Show that if you have two edges with the source of E and the range of F different, so you can't concatenate them as paths, you can't put them together as paths with what is it? with F on the front and E on the back. Show that FE is equal to 0. Sorry, give me a moment. My goodness. All right. Sorry about the disturbance. We'll keep going. So the really important property of Leavitt path algebras is that these relations here allow you to say something very strong about the structure of the finitely generated projective modules. There's a very visual interpretation of what this monoid is, and we'll lay it out here. So the graph monoid is just a monoid that you can associate to any directed graph. It's a free monoid generated by the vertices, and they're subject to the relation that a vertex V is identified with the sum of vertices which proceed from it. So to give you an example here, we're using this same monoid up here. We label these V, W and U. Then in the graph monoid of this thing, it would just be the monoid generated on symbols UVW. So I guess we can say natural numbers. I don't know how we'd write this. Span of the natural numbers V U W, subject to the relation that V is equal to U plus W. So that's the graph monoid there. And the property here is that the projective modules is isomorphic to this graph monoid. It's a fairly involved proof. I think the easiest way to do it is via the technology introduced by George Bergman in the 60s. You can read this paper if you want to really appreciate this. It's a difficult paper, but sections 5 and 6, when you read them a few times over, give you some of the most beautiful algebra you've ever seen in regards to projective modules. And his article essentially states, he introduces what he calls a conical monoid. Basically, a conical monoid is just a normal commutative monoid with the property that if x plus y is 0, then this implies that x and y must both be 0. And the second property is that you need a distinguished element I in your monoid, such that for all x in your monoid, you can find some integer. So some integer n and some other element of the monoid, such that x plus y is equal to a multiple of this distinguished element I. So basically, you can think of it as stably all things in X, or all things in the monoid M can be related to some distinguished element. And the key idea in Bergman's paper is that if you give me any monoid like this, and you give me any field K, I can construct a K algebra whose projective modules are isomorphic to this monoid, the finitely generated projective modules. And his methods also gave you a weakly universal way to construct such an algebra. And the idea here is that if you apply his technology to this graph monoid, you will get the Leavitt path algebra. So this gives us a nice kind of weakly universal property of what the Leavitt path algebra is. We're not going to use this in our school in the little seminar we'll have in India, but it will give you, it's just some background knowledge for you to know about why Leavitt path algebras are so interesting. So also, I'll say a few things about K theory, and then we'll get into the non-essential stuff that I find quite interesting. The idea with K theory is that we're interested in the category of finitely generated projective modules. We're not only interested in what projective modules there are, but also the structure of isomorphisms and automorphism groups in there. And what we do to define algebraic K-theories, we take this category and we take out all the things in there that aren't isomorphisms. So we're just looking at the category of finitely generated projective module with its isomorphisms in there, and we construct a very complex topological space, and we take its homotopy groups to be K-theory. Other kinds of K-theory out there, topological operator K-theory, K-theory of schemes, these all revolve around the study of some object that behaves very similarly to projective modules. So I'm not going to go into more detail here because I don't have time. But if you ever done topological K-theory, for instance, you're interested in vector bundles. And by Swan's theorem, vector bundles are basically the same thing as projective modules over a certain algebra. So that's all the essential stuff done. So if you have been, thank you for listening. Otherwise, if you want to keep listening to me ramble on about things that I find interesting, you can stick around. So I want to talk a bit about category algebras and how you localize them. And my aim here will be to show you how even this very different approach gets you Leavitt path algebras. So here we're going to have a field K, and we'll make up a word for it. We'll call it a K category. It's just a category enriched over vector spaces whose objects form a finite set. For our purposes, we'll say a finite set. So when we, by the way, if you don't know what I mean by enriched, it means that all Hom sets are vector spaces over K, and composition is a bilinear map. So, and from this we form the morphism algebra. So the elements of PKC are formal sums of morphisms, and multiplication is given by concatenation if you can concatenate, and zero otherwise. Very similar to the path algebra, if you've seen that before. A related notion, which we'll talk about, is algebras with a complete set of orthogonal idempotents. So by this we mean a pair where R is a K algebra and I is a set of orthogonal idempotents subject to this constraint here. For our purposes, we're also not going to require that the idempotents are primitive. By primitive, I just mean, I'll write this down quick. We say an idempotent is primitive if E can't be written as F plus G for Fg in R, non-zero, I guess I'll say orthogonal. Oh, I can't write today. Orthogonal idempotents. So if you can break E down into the sum of two mutually orthogonal idempotents that are non-zero, E is not primitive. If you can't do this, then E is primitive. So as an exercise for you, try and show that if this set is finite, this set I is finite, then if you take the sum of all the idempotents, this will be the identity in your algebra. And here's a condition for what orthogonal means. I think I've mentioned it already. Forgive me if I haven't. And the theorem here is that there's a one-to-one correspondence between K categories and algebras with a complete set of orthogonal idempotents via this correspondence here. You take your your K category, and you spit out this morphism algebra, and the orthogonal idempotents are the identity morphisms. So you recall we require this to be a set. So the objects of C can't be a proper class for this correspondence to work. As an exercise to you, I want you to try and construct the inverse correspondence. So to give you a hint, these things here should be your Hom sets. And I'll let you think about what the object should be. So we call two idempotents equivalent if there exists ring elements AB with AB being E and BA being F. Why we say it's a bit of a weird condition when you see it for the first time. The idea is that in the same way, we say that two objects in a category are isomorphic if you can find morphisms between them, which are mutually inverse of each other. It's the same idea here. So if you're able to construct this correspondence here, and you translate over what it means for two idempotents to be equivalent, you'll actually see that idempotents being equivalent is the same as kind of the corresponding objects in the category being isomorphic. But I'll let you write it out in full for yourself as an exercise to see what I fully see what I mean. So if you recall earlier from what we said that projective modules are just images of idempotent matrices. If we have equivalent idempotents here, it'll also correspond to isomorphic projective modules. Same idea. So this RE and RF are direct summons of the free module of rank 1. This idea also works if you replace E with, say, a 2x2 or a 3x3 idempotent matrix. The same can still be said, but I just wrote this for simplicity. So what we have now is a recipe for making projective modules isomorphic by adding generators and relations. If we have two idempotent matrices and we want to make them equivalent, we can just formally add elements to our algebra in this kind of way with these relations to make the corresponding projective modules isomorphic. And since we're able to kind of formally add things to make stuff isomorphic, this gives us a recipe for localizing categories. So if you don't know what a localization of a category is, we'll go through it now. So if you just have any category and any morphism that you want to turn into an isomorphism, we can define this CF inverse to be the localization. The universal category with this property that if F here is a functor into a category D, such that F of F is an isomorphism, then F will factor uniquely through an embedding. So localization in general is a very difficult problem. If you've ever studied, say, model categories and high-level homotopy theory, a lot of the difficulty due to that in studying that theory is due to the fact that you're trying to localize with respect to weak equivalences, if you know what that is. My point being that if you want to localize a whole bunch of morphisms, it's not always clear that what you'll get is even a category with any well-defined sense of what a morphism is. But in this case, when you have the setup we had earlier, where you have K categories with a set of objects and a single morphism you want to invert, it's always possible. And we're going to show you how to do it here. So the recipe is you can take a K category C, and you spit out its category algebra. And if this morphism in C is what you want to invert, you let X and Y denote the idempotents corresponding to the identity of X and Y respectively. Then the morphism F lies in this part. of your category algebra. And so we just formally adjoin an element G subject to these relations here. That is to say, G lies in X, R, Y. So I'll write this out. G lies in X, R, Y, and GF is equal to X, FG is equal to Y. That is to say, we've just added an element such that X and Y are now equivalent. Can't write it out. Are equivalent by means of F and G. And the K category corresponding to the resulting algebra R prime with the same objects is the localization of this C with respect to F. So we basically, we did the localization problem purely by translating it to the setting of algebra. And then we pulled it back to the setting of K categories. That's quite interesting there, I think. So to show you an example of this, we're going to construct the Leavitt path algebra using this idea of localization. So for a field K and a directed graph, we can form the path category. So objects are just formal sums. Let's typo there. So I'll just say here, the objects are formal sums of vertices in E0. I'll write that in. Wait. Draw. Okay. Formal sums of write it in. Vertices. Very good. The objects are formal sums of vertices in E0, and morphisms between two vertices are formal k-linear spans of paths from V to W. And morphism and composition is just path concatenation. So what you can do with this path category is you can formally invert certain morphisms. So if we have a morphism from V to the direct sum. Wait, no. So E in. Okay, there we are. So we have a morphism from V to the things coming out of V, the vertices proceeding from V, via, let's see, it's just going to be the direct sum of edges. So you recall that an edge is a path of length 1, and the path, this path here, is a path from V to whatever comes out of V. So this is a well-defined morphism. And what we could do is we can form the category algebra in this way. And if we localize with respect to these morphisms here, you can actually get the Leavitt path algebra. If you want to give it a try, do it for yourself. There's some nuances here which I haven't fully gone through due to time constraints. So you can give it a try if you want, but for instance, these don't form a finite set. For instance, if we take formal sums of vertices, the way you have to do it is you have to go to the level of matrices. And well, matrices of arbitrary size to make it all work properly, but it can be done, and you'll get the Leavitt path algebra. And for the last little bit to finish us off, so this is a formulation of Leavitt path algebras I quite like, and it's a way of looking at things that is useful for representation theory. So if you have a K category with a category algebra PKC, there's a categorical isomorphism between the category of K-linear functors from C to K vector spaces and the category of, say, left PKC modules. So there's a categorical isomorphism between these two things. It's passed from functors on the side of categories and module or representation theory on the algebra side. It's not a very useful computational result, but it is a good insight if you want to study representation theory of algebras which have a nice categorical interpretation. So as a final thing, I'll show you what this insight provides you with. We have the n-rows graph. So if you don't know what the n-rows graph is, it's just a graph with a single vertex and n loops. And I'll try and see for yourself if you can figure out why the Leavitt path algebra associated to this directed graph here has no finite dimensional representations other than the zero representation. So have a think about it and pause the video because I'm going to tell you the answer soon. The answer is that if we label this vertex V, then since on the categorical side, what we've essentially done is that, remember, we have, how do I say this? Essentially, all these n loops give you a morphism on the category side from V to n copies of V. And recall the Leavitt path algebra is formed by localizing with respect to this. So this means that the part of the vector space, when you look at the representation of this thing, the part of the vector space corresponding to V should be isomorphic to n copies of V. So finding a representation of the Leavitt path algebra of this thing really amounts to finding a vector space V that is isomorphic to n copies of itself. And we can very easily see why now you're not going to be able to do this if this vector space corresponding to V is finite dimensional, unless V is 0. So that's all we have for now. I look forward to seeing you all in India. Adios.